Okay, welcome back everyone. In this section, what we're going to talk about are machines. It's basically the same thing as frames. And in fact, if you look at the previous video, I lumped them together as frames and machines. But as it's somewhat of a complicated topic, I figured I would go ahead and make another video. At least that way you get one more example. There's not too much to talk about the process, but more examples are helpful. So what's the difference between a machine and a frame is the only real difference is the machine has some kind of input forces that will result in output forces, or it's doing work if you remember that from physics. So for an example, I have a pair of pliers here. I can see that I can break them apart at the pinned connection between these two lever arms. And when I break it apart at a pin, down below I can see I'm looking at the upper arm. And at the pin I have a reaction in the X and the Y direction. And I still have my external force that I'm applying, P, and my reaction onto the object of Q. And you could develop a relationship between P and Q, which is called your mechanical advantage. Not really the topics that we need to be concerned about. We're going to be looking more at just finding out forces on the object, not so much mechanical advantage. So let's go ahead and take a look at an example. In this case, we have this press that's used to emboss the seal at E, and we know we're pulling down with a total force of 250 newtons. We want to find the vertical force onto the seal and also the support reaction at A. And we want to know something like this in the real world because we need to know, maybe we have to design the length of the lever arm in order to get the right pressure onto the seal, or designing the pin to make sure the pin isn't going to shear at point A. So the first step, just like in frames, is to say, are there any two force bodies here? And I do identify a two force body between B and D because it's pinned on two ends, no forces in between. That means I know my force along BD. And once I know that, then it's easier to figure out what I'm going to draw from my free body diagrams. In this case, I would say I'm going to draw two free body diagrams, one for that object at D and another one for that lever arm A, B, C. So those would look something like this. Alright, so the way I broke this down is I looked at this part D, and I knew that two force body BD, so I know its direction has to be 20 degrees from the vertical, which I can see I put that force pushing down on that whatever you call that thing, that embossing member. And then I have force at E is the force that's pushing down on the seal, and then I have a normal force that's pushing against the side of the wall. I need to have something there to balance out those forces. The other free body diagram would be of that lever arm, and the FBD would be equal and opposite, so 20 degrees from the vertical once again, but pushing up towards the arm. Reaction at A has an X and a Y component, and then I'm pulling down in the end with 250 newtons. So if I look here, looking at free body diagram 1, I have three unknowns. Free body diagram number 2, I have multiple unknowns, but I have FBD as common between the two of them. So I decided to look at free body diagram 2 first. And the reason I decided to look at that is because I could solve for that FBD by taking the moments about point A. So if I sum the moments about point A, maybe I should draw it over here so you can see it a little bit better on where these numbers are coming from. I'm just going to quickly sketch it out. Alright, so in essence what I'm doing is I'm putting everything in my X and Y directions and looking at their respective lever arms. So I have FBD sine of 20. Of course, that would be my horizontal member pushing this way, and I should do it in red so we can see it. And then I would have a lever arm of 200 sine 60, so this would be that vertical distance there. And then I'd have the FBD cosine of 20, so then I'm saying, well, what is the vertical force? And of course then I'd be looking at this horizontal lever arm. That's my 200 cosine 60. And then I have the 250 on the end, and I need its lever arm, so the distance all the way from A over. So I have two parts to that. the 400 cosine 15 and plus the 200 cosine 60 to get that total horizontal distance for that vertical force at 250. Punching into my calculator, solving for FBD, I ended up with a force on that member BD, that two-force member, of 793.64 newtons. But that was not the question. The question is, what is the force exerted onto the seal? But once I have that part, now I can move over to free body diagram 1 and say, what's pushing down on this seal. And from this guy, it's pretty easy. I just have to do sum of the forces in the y direction equals 0. So I have this Fe pushing up, which is what I'm looking for, minus this force pushing down, the 793.64 newtons, but I need the vertical component. So I'm going to take the cosine of 20 times that, set it equal to 0, and I can find the force at E on that seal to be 746 newtons. Of course, it's pushing down onto the seal, and that's what it was asking for in part A. Now, part B, we really could have solved part B from the very beginning, because part B is saying what's the reaction to A. I'm going back to that second free body diagram. Once I know the force in BD, I just can sum the forces in the x and y direction. So I guess this is technically part A and part B. I didn't really label it that way, but part B, let's go back to our free body diagram 2. And with that, summing the forces in the x direction equals 0 gives me an AX, let's see, minus the force in the two-force member, 793.64, but I want just the vertical, or sine 20 of that force, set equal to 0. And I had a reaction at A in the x of 271.44 newtons. And from sum of the forces in the y direction equals 0, same idea. I have AY going up, and then the component of that two-force body, 793.64, times the cosine of 20 equals 0, gives me an AY of 495.78 newtons. And I got a negative number, so it's actually pointing down. This one was positive. I could combine that into a single force. I do that in the notes if you want to see that. It's just that using Pythagorean theorem. One last little step, not really overall important, unless you were designing the shearing stress on that pin, and then you would be looking at an overall force. So hopefully that problem was a little helpful in explaining how you're going to break these things apart. Every one of these, just like frames, are a pain in the ass. Every single one of these is different. So you need to break them apart, identify those two-force bodies. When you find a two-force body, you know its direction, and solve for what you can solve, and you might have to hop back and forth between different free body diagrams for the parts and pieces of your machine. So that's it for now. Let me know if you have any questions, comments. Otherwise, I will talk to you later. Thanks.